In this video, I want to take a look at an algebraic approach to the dot product. It seems like every other book I've ever used for linear algebra, or Calc 3 for that matter, working with vectors, um, every other one seems to use the geometric approach as the definition, and then the next one uses the algebraic approach as the definition, and then somewhere they need to show that they're actually the same thing. So I'm actually, for these videos, showing them both as definitions, and then we'll prove that they're the same, right? That they actually are calculating the same thing. So here's the algebraic definition of the dot product. So suppose I've got two vectors, u and v, in Rn. Then I'm going to define the dot product as u1 v1 plus u2 v2 plus u3 v3 and so on all the way up to un vn. So take the first components, multiply them together, take the second components, multiply them together, third components all the way down to the last one, and add the results. Now, please note that it is add the results. I see a lot of students do this, and they multiply these together, and they multiply those together, and they do all those multiplications, and then they put commas in between to make a vector out of this whole thing. It's like, whoa, wait a minute, wait a minute. The dot product is supposed to give us a number, not a vector. And you see with it defined as I have here, it is giving us a number, because all of these u1, v1, u2, v2, and so on are numbers. You multiply them together, you get a number. You add all those numbers up, you get a number. You're not getting a vector here, right? Here's an example in R4, 2, 4, 1, 5, 3, 0, minus 5, 2 are my two vectors, and I take the dot product. So the first components are 2 and 3, multiply those together. The second components are 4 and 0, multiply those together. Third components 1 and negative 5, and fourth components 5 and 2, and then add those results. So I got 6 plus 0 minus 5 plus 10 is 11. The dot product of these two vectors is 11. Now, what does that actually mean? We'll get to that. We'll get to that. Not in this video, but in one very soon. Here's the example we did last time, where I drew these vectors and just gave you the lengths. I didn't actually give you the coordinates. Well, I can give you the coordinates here in that if I drop a perpendicular, oops, let's draw that perpendicular a little better. I drop a perpendicular here, that this was supposed to be a 30, 60, 90 triangle. So this length here was 3, and then multiplied, so this was 3 root 3. And likewise, for this one, if I drop the perpendicular down, that was 4, so the x component down here was 2, and then this was 2 radical 3 up here. So the dot product, so there's the two, so the first one, u, is the x component was 3 radical 3, the y component was 3, and this was 2 and 2 radical 3. And so when I look at the dot product of those two, multiply the first together, multiply the second components together, and I get 6 radical 3 plus 6 radical 3 is 12 radical 3, which is exactly what we got when we looked at this with the geometric approach. Okay. Now, notice that it produces a number, and that the order doesn't matter, right? Again, where's the actual definition? Let's scroll up a little bit. Right, the fact that it's u1 v1, it could have been v1 u1 and v2 u2. That multiplication is commutative, so it doesn't matter what order you multiply each of those in. So it doesn't matter which order the u and the v are. So u dotted with v is going to be the same as v dotted with u. And one thing I want to end with here is a theorem that this definition also has the property that if I take the dot product of a vector with itself, that I get the length squared. So if I take the square root of that dot product, I get the length of the vector, or the norm of the vector, right? And the proof is pretty straightforward, because u dotted, the square root of u dotted with u is the square root of, well, instead of u and v, I have u1 v1, u2 v2, u3 v3, all the way up to un vn, and there's plus signs in between all of them. And so that's the sum of u1 squared plus u2 squared plus u3, and that's under the square root. And that's exactly what the definition of the norm of u is in Rn. So yes, indeed, this is satisfying that same property that the geometric definition satisfied. That the Dot product of a vector with itself is the length squared, or the norm squared. Okay. What we need to do now is to show that indeed these really are the same process. And that will happen in the next video.